Section 5.6 introduces us to the formal definition of the definite integral from a to b of f of x dx. We've spent several sections getting to understand this definite integral as signed area. So if that were our function y equals f of x, and maybe this is a and b, we know that this is the signed area now between the vertical lines x equals a, x equals b, the x-axis, and the curve itself. That is the definite integral, and that's not going to change. But we're going to give a more formal definition that can be used to prove other theorems, and also, very importantly, can be used to estimate definite integrals for which we do not know the formula for its antiderivative. First, we're going to define a Riemann sum. A Riemann sum is an estimate of a signed area. And first, to get the estimate, you have to take the interval AB and you partition it or break it up into little subintervals. And for generality, we'll say n subintervals. So we let A be called x0 or x0, and let's, for simplicity, break it up into n equal length subintervals. So x1 would be the first partition point, x2, x3, and so on. I'll kind of put slash marks here to say we don't we'll just call this one the x sub I minus 1, x sub I. So this is the ith subinterval right here. Notice the first subinterval had x1 as its right endpoint. The second subinterval has x2 as its right endpoint. And the ith subinterval, for generality, has x sub I, the ith partition point, as its right endpoint. And we would keep going until we get to the end, and this would be x sub n minus 1, and we call b x sub n. So we have partitioned the interval AB into n equal length subintervals. Now, if they're equal length, it's just natural for you to see that delta x, or the width of each subinterval, will be the length of the interval b minus a divided by the number of subintervals n. So delta x is b minus a over n, and each one of these little intervals is of width delta x. Now we want to estimate the signed area under the curve from a to b. So in each one of these little sample points, subintervals, we're going to pick a sampling point c sub I. So I'll pick a different color for that. And it doesn't really matter where we pick them. Maybe I pick one in the first subinterval, I'll call that C1. And I'm going to pick one in the second subinterval and call it C2. And one in the third, C3, and so on. And in the ith subinterval, I'll choose C sub I. And in the last subinterval, I'll choose C sub n. There's nothing special about where these are chosen as far as this definition of a Riemann sum goes. C sub I can be chosen anywhere in the ith subinterval, including it could be equal to the left endpoint, the right endpoint, the midpoint, or any other point in the subinterval. Now, why did we choose those? Well, we're going to use each sample point to go up to the curve and get the point on the curve corresponding to that sample point. So, for example, this would be the point C1 f of C1. And this point going up from my second sample point, this point here on the curve will be C2 f of C2, and so on. So let's do it on the general subinterval here, the ith subinterval. I go up, I grab the point C sub I f of C sub I. And I keep doing that all the way to the last subinterval, and I grab my point C sub n f of C sub n. Now those points there are going to determine the height of rectangles. Over each subinterval, we're going to construct a rectangle. I'll change colors again. Let's see, maybe go back to white. No, yellow. Alright, so over the first subinterval, from a to x1, I'm going to use that point that I got as its height. I'm going to use the y-coordinate of the point as the height. So the second subinterval, I use f of C2 as the height of that rectangle. So each rectangle, here's f of C3, each rectangle has width delta x and length f evaluated at the sample point. So our generalized one, we have f of C sub I is the height, and the width is the same all the way across, delta x. So the area of this rectangle right here, the area of that rectangle is delta x, the width, times the height, f of C sub I. That's the area of that rectangle. The last rectangle using f of C sub n, there's the last rectangle, and you can imagine all n of them. Now, if we add up the areas of those rectangles, of course we get an estimation of the signed area under the curve of f of x from a to b. So this is called a Riemann sum, the sum of the areas of those rectangles. So right here is your Riemann sum. Notice the area of the first rectangle would be f of C1, its height, times delta x, its width. The second rectangle, f of C2 is its height, times its width, delta x, plus dot dot dot, oh there should be a plus there, plus f of C sub n, delta x. This is called a Riemann sum, and as you will see in the book, this will usually be expressed in sigma notation. The sum from I equals 1 to n, I equals 1 to n of f of C sub I delta x. Okay, so let's do an example and you'll catch on. That was a lot of notation on that last drawing, and you'll get used to it. Just look at an example. Don't memorize something like that until you completely understand it. Alright, so we want to estimate the signed area, the blue signed area under the curve natural log 1 plus x. Okay, so it says estimate the signed area by using a Riemann sum with 5 equal width subintervals and midpoints chosen as sample points. So we see, well, this is pretty easy, isn't it? It goes from 0 to 5, and our delta x, we're using 5 subintervals, so convenient for us, delta x is equal to 1. 5 divided by 5, the length of the interval divided by n. n is equal to 5 here. Alright, so let's pick the midpoints of each one. as our sample points. That's C1, which is 1/2. And this is C2, which is 3/2. 2 is 4/2, C3 is 5/2. 3 is 6/2, 7/2 is C4, and 9/2 is C5. We're just picking our sample points, and we go up above each one and grab the point on the curve. This is 3/2 f of 3/2. 5/2 natural log of 1 plus 5/2. 7/2 natural log of 1 plus 7/2. 9/2, and the height is the natural log of 1 plus 9/2. And we use that y value to construct our rectangles over each of the subintervals. Sorry, I'm not good at drawing with this on this. That's about as best I can do, but you can see, hopefully, that these are rectangles, and they're supposed to be all the same width. So we have 5 rectangles of width 1, and our Riemann sum is the sum of their areas, the red areas. You can see it's going to already, just with 5 rectangles, it's going to be a pretty good sum. And so how would we then calculate the sum? The sum is the Riemann sum, and we would write S5 So we have S5, n is equal to 5, Riemann sum. So we have f of 1/2. That would be the natural log of 1 plus 1/2 is 3/2. Times 1, so I won't put the plus 1 in. And then times 1. Then we have the natural log of 3/2 plus 1 would be the natural log of 5/2 times 1, plus the natural log of 5/2 plus 1 is the natural log of 7/2 times 1. Delta x is 1, so I'm not putting it in. The natural log of 7/2 plus 1 is the natural log of 9/2. That times 1. Plus, and the last rectangle is the natural log of 9/2 plus 1, natural log 11/2, and that is times 1 delta x. If we wanted to, we could factor out the delta x and just write it right here so we would remember that. And when I put this into my calculator, I get approximately an estimation of 5.78. So that's our estimate of the area under the curve, the actual signed area. Okay, we're going to do the same example, except this time we're going to use a Riemann sum with 5 equal width subintervals and left endpoints chosen as sample points. So we have the same 5 intervals, n is equal to 5, and delta x again is conveniently just 1. And we're going to use the left endpoints. So let's see, I'll go do it in red again. So the first subinterval is from 0 to 1, and we're going to use C1 equals 0, this first sample point. The second subinterval is from 1 to 2, and we're going to use its left endpoint as C2. So this would be C2 equals 1. C3 is 2, C4 is 3, and C5 is equal to 4. We're using the left endpoints. So we go up above each one and grab the point on the curve right above it, because that's going to determine the heights of the 5 rectangles. the left endpoints. So we see here the point 0, 0 is on the curve. We get no height at all, so we don't get any area there of any rectangle. On the second subinterval, we use the height of the left end at the left endpoint, and the third and the fourth rectangle. You see we're going to get quite an underestimate here, aren't we? So we have our just really four areas here, because the first one didn't give us a rectangle. Adding up the areas of those rectangles, we get what we call a left Riemann sum. So let's see, we get 0 for the first one, 0 times 1, 0 times delta x, plus the function evaluated at 1, which would be the natural log of 1 plus 1 is 2, times 1, times delta x. Last time I didn't put in the ones. This one will be the natural log of 2 plus 1, or natural log 3, times 1 delta x, plus natural log 4 times 1 is delta x. So we have 1, 2, 3, 4, and our last one is natural log 4 plus 1 is natural log 5 times delta x is 1. So I'll figure this out on my calculator again. And I got approximately 4.78. So you see this is a much smaller estimate, and you can see in the picture that indeed it is a low estimate for the actual value. Now I won't be able to write on this, but I can show you what Mathematica does with this. I integrated, you see you have the same curve there, y equals the natural log of x plus 1. And the signed area under the curve, I can point to it here for you, Mathematica integrated it for us, and the actual integral is 5.75056. And this estimate, well, this is using just two subintervals. This is a Riemann sum, and you can see that it's using left endpoints for sample points, because the first of the two did not give us a rectangle. The height is 0. But the second one is using the height at 2.5. And we just have one rectangle, and we see that we certainly get a very low estimate. So watch what we can do. I can move these are left endpoint sums. Let's increase the number of rectangles. Now we have 3 rectangles. The Riemann sum is 4.07. We can see it would be way too small. It's 1.67 off. Notice the error is right here. If we increase the number of subintervals, now we have 4. And now we have 1, 2, 3, 4, 5, 6, 7. And you see that the error is getting smaller. With just 7 rectangles, we're getting a pretty good estimate. The integral is 5.75, and we're getting an estimate of 5.07. So let's just go up one at a time. There we have 7. And there's 8 rectangles. Let's go until we get an error of less than 0.1. So we have to go up further. Notice we're just using left endpoints. Here we have 12 subintervals, using left endpoints as our c sub i's, and we're off by about 0.4. So I want to keep going. I can get whatever accuracy I want. I just have to increase the number of rectangles. And watch how the estimate is becoming better and better. And I want to go there. Now I have it at least 0.19. I can get that degree of accuracy with 23 rectangles. Let's go to midpoint sums. Now, let me go back. Let's go back to 5, the one we did. There's 5. That's one that we did, and we got 5.78 for our estimate, and the integral is 5.75. So these midpoint estimates are better, but and so all that means is that we won't have to go up as high to get within point. Oh, we only have to go to 6 rectangles here, and we have 0.02 error. And you can see why. The amount of blue rectangle the overestimate is about the same as the white areas here. Each one, the white and the blue, is almost the same. So granted, the midpoint intervals do better on this particular curve. We also could use right endpoints, and we're getting estimates that are too big. But even with right endpoints, as we increase the number, look at what happens. Increase the number of intervals, and when we get to 30, we have a 0.14. We could go up to 50 rectangles and have 0.08. Look at those, hardly any error at all. And if I go up to, let's go all the way up to maybe 100. Could I go that high? Let's see. Yep, there's 100 rectangles. And look at that, there's hardly any error at all. And what I want you to see here is that if you are using Riemann sums to estimate the area, the signed area, or the definite integral, it doesn't matter which you pick for your sample points, midpoints, endpoints, or throw a dart in the interval. You can pick any c sub I in the ith subinterval. And regardless of how you pick your sample points, all you have to do is keep raising the number of subintervals, enlarging the n. And as you make n bigger, then you can get any degree of accuracy you want. So with that in mind, this is, I think that you will understand the formal definition of the definite integral from a to b of f of x dx. Remember, I told you that all new concepts in calculus, calculus 1, 2, and 3, anything past pre-calculus, everything is defined in terms of limits. And so, let's read the definition. Let f be a function defined on the closed interval ab. Then let x0, x1, x2, comma, up to xn be a regular partition of the closed interval ab. That means regular just means that they're equally spaced. Delta x is the same on all the subintervals. So you partition the interval ab into n equal length subintervals. And capital S sub n, which is, notice how we read this, S sub n is the sum from I equals 1 to n of f of c sub I delta x, be a Riemann sum for f. Now we defined a Riemann sum before, so you know that the c sub i's are the sample points taken in the little subintervals. The definite integral of f over ab is equal to the limit of the Riemann sum as n approaches infinity. Or we can write the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I delta x, if this limit exists. Now all of the examples that you will study in Calc 1, 2, and 3, or I should say just Calc 2 and 3, this limit will exist. Also notice that this sigma notation, Sn, write it the other way for you too. Sn is f of c1 delta x plus f of c2 delta x plus all the way up to and ending with f of c sub n delta x. So the I here is a counter, and it tells you to just add, starting at I equals 1, then add, change, let I equal 2, I equal 3, I equal 4, up to I equals n. So that's it. That's the definition of the definite integral, and you can try your hand at doing some Riemann sum estimates and just making sure that you understand this definition before we go on.